For letter G, this n factorial squared, I would write it the following way. Limit of n factorial times itself divided by n minus 1 factorial n plus 1 factorial. Okay, so what I would do here is group these two and group this other two. Okay, so from the first group, the one that I highlighted in yellow, which of the two factorials is the larger one? The one on the top or the one on the bottom? The one on the top, because n is large. This n right here is larger than n minus 1, so we will expand this one right here. And this is equals to limit n times n minus 1. Well, this one matches the one in the denominator times. Now let's look at the factors highlighted in green. Well, so between n and n plus 1, which one is the largest one? N plus 1. So let's expand over the n plus 1. That is n plus 1 times n, which is 1 less than n plus 1. And that's an n plus 1, n factorial rather. And we're ready to divide out factorial factors. This one's right here and this one's right there. Leaving us in this case with the following. That's the limit and that's n over n plus 1. And well, in this case, well, the degrees on both numerator and denominator, they're the same. Ratio of leading coefficients is 1 over 1, which is 1. Therefore, the sequence happens to converge. Letter H, ln of n over n. Let's write it first of all as a limit. All right, let's compute this limit. So on the one hand, okay, where is ln going as n approaches infinity? And the denominator also goes to infinity. Well, that means this limit is a good candidate for L'Hopital's rule. So let's take the derivative of ln of n. What's the derivative of ln of n? 1 over n divided by the derivative of n, which is simply 1. Which, okay, let me rewrite this, simplify. This is the limit 1 over n approaches infinity. And where is this limit going to go to? 0. Which means the sequence converges. Also, from the growth rates, we could have done this using the growth rates, because, well, n is a polynomial and polynomial grows faster than a logarithmic function. That's another way. But for this one, I would require to do just the L'Hopital rule more specifically. All right. Other properties of sequences, monotonic and bounded sequences. Well, these are more like terms that will be useful later on in analysis. And I mean, these come directly from or get connected with the fact that functions or the related functions that look like are either increasing or decreasing. And I mean, let's write, well, the graph of an increasing function looks like this. But in this case, we're not looking at a function. We're at a function of real numbers. We're looking instead at a function of sequence of numbers in this case. So, for example, this is how the graph of of a sequence looks like. Alright, and well, let's choose any random point. This random point in this case, let's call it a sub n. Whatever that is. It could be, this a sub n represents the nth term, like the 5th term, the 7th term, the 75th millionth term, whatever term you want, that's fine. That means the next one would be the term a sub n plus 1. Okay, so from this graph, looking at the heights on this function, clearly a sub n plus 1 is a quantity that is larger than a sub n. Do we all agree with this from the picture? Well, so for this reason, a sequence is increasing when a given term is less than the next term, the n plus 1 term. So from here we can see that it's increasing because a sub n is less than a sub n plus 1. And of course, the picture just changes for a decreasing function. And in this case, well, choose just a random point. I'm going to choose this one as an a sub n. And again, can be any, the 3rd one, the 5th one, the millionth one. This is the n plus 1 term. But in this case, notice how in this time, the a sub n plus 1 is a smaller quantity than the previous one, a sub n. Well, number one, from the picture, this supports this idea right here. In this case, a sequence is decreasing when a given term is greater than the following term. So this is decreasing because a sub n is, in this case, greater than a sub n plus 1. Alright? I mean, it's nothing, it's really not, the idea is really nothing new except for we're doing this picture for the graph of a sequence as opposed to the graph of a function like you did back in Calc 1. So, let's do one example and show that this given sequence is decreasing. So there's a couple of ways to do this. Number one, write down the corresponding function of x, take the derivative, look at the first derivative test, you will find out that it is decreasing. The other way, this is not necessarily valid because, I mean, you look at this, yes, well, it's decreasing, the n's are in the denominator, get big, and well, but we still need to show this in a more formal way. How? Using an argument like this. Right? So, let's first of all set our a sub n to be 1 over n squared plus 1. So that's our given sequence. We're going to do the following. Shift that n to n plus 1. So a sub n plus 1, 1 over n plus 1 squared. Alright. And then from here, what we're going to do is put these two together. So I'm going to write a sub n versus a sub n plus 1. So on the left-hand side of the inequality, I'm going to write simply a sub n, 1 over n squared plus 1. And on the other side, n plus 1 squared. Okay, in this case, which inequality symbol should I put? This one, perhaps? I believe... Okay, this one. Because, well, this quantity looks greater, but it's greater in the denominator, making the overall quantity... So this one is fine. And well, because we were able to show this inequality, this is enough argument to say, hey, it's decreasing. Because we're comparing the nth term with the n plus 1 term. That's all we need. This is enough argument. So doing it with numbers doesn't really, that's not the correct way to That's not a valid argument. Like, for example, saying, oh, okay, let me choose n equals 1 and then n equals to no. That's not. We need to show it in a general way that involves n in a more formal way. Okay, more definition. So sequences are bounded above or bounded below, or are simply bounded whenever. Well, for example. So we're going to have a sequence with increasing values. For example, it's increasing, and it will asymptotically get to maximum value. It may get to that value, it may not get to that value. Well, it depends. And for a sequence that it's bounded below, we're going to have most likely a decreasing sequence for which it's going to get some value. However, a sequence is simply bounded, or rather, or if it's bounded both above and below, we just call it bounded. Okay, so let's have. I mean, it's like a lot of words, but let's have a look. Let's have a look at a couple of examples. And well, so the first thing we do is find the limit. 2 plus e to the negative n over 3 as n approaches infinity. Well, what do we have in this case? In this case, we have an exponential function that happens to be decreasing. How do we know it's decreasing? Because of the negative sign in the coefficient. So this looks like this. All right. However, this exponential, because of these two right here, this means it's shifted up 2 units. Okay, so the original exponential function looks like this, right? Even though we don't draw this usually, but technically, there is always this invisible asymptote in there, right? The x-axis, in the same way that the logarithm function, the natural log function, or any logarithm function has a vertical asymptote at the y-axis, right? But we rarely draw those asymptotes. Well, so when we shift the graph of the exponential by 2 units, we also shift the location of that horizontal asymptote, in this case, by 2 units. All right, and well, let's give this function a character of a decreasing one by just drawing it this way, right? So yes, I mean, when we compute this limit, this really goes to 0. The limit is 2. All right, but I mean, just computing the limit doesn't really tell us anything about it's the nature of its boundedness. In this case, whether this function is bounded above or bounded below. The best way to get to see that is looking at the graph. So in this case, yes, it's bounded at 2, but in this case is bounded below by, and in this case it's lowercase m for the lower bound, for a lower bound. All right. Let's look at the next one. Let's look at the sequence arctangent of pi n. That's the limit. Let's write it as a limit problem. Limit of arctangent of pi n as n approaches infinity. Well, in this case, it's important to recall how the graph of the arctan function looks like. Well, so I'll write it down over here. So let's draw the graph. Recall, it looks like this, with horizontal asymptotes like this. All right. Now, looking at the graph of arctan and computing the limit, Well, of course, what's the limit? Number 1. Pi over 2. Pi over 2. So, but the question here is this sequence bounded above or bounded below? Or bounded both above and below? So do we have an upper bound, or both bounds above and below? It's just an upper bound, so don't be fooled by the picture. Yes, clearly from the picture we have a limit above and we have a limit below. However, look at the region that we're interested in. So from this region right here, the only limit at infinity, it's the one above. So bounded above by, in this case, big M equals to pi over 2. All right, let's see. Let's look at the next example. Sine pi over 2n. Yes?
So, would we have, if we had a negative value instead, we just focus on the value below?
Exactly. So, for example, that's a good question. So, if in this case we had this arctan of pi n, but in this case going from n equals negative infinity to positive infinity, then we would be looking at both bounds. But because we're looking at the end behavior of the sequence, in this case only towards the right side, so towards the right side the bound is going to positive pi over 2. All right, let me erase this, and all right, sine pi over 2n. Let's have a look at this one. Limit sine pi over 2 n as n approaches infinity. All right, let's see what's going to happen here. Any ideas about this one?
Is it bound by both?
Bounded by what?
Bound by both?
By both? Both. So we're going to have both upper and lower bounds, bounded above, bounded below. So this one will simply call bounded. Let's see. Okay, so let's look at the graph of this. Okay, so sine, okay, at n equals 1, that's sine of pi over 2. What's sine of pi over 2? 1. Okay, for n equals 2, that means sine of 2 pi over 2, which is sine of pi. What's sine of pi?
0.
Okay, the next one, n equals 3, that means sine of 3 pi over 2, which is? Okay, the next one, sine of 2 or 4 pi over 2, which is sine of 2 pi. What's that? And well, did you see where is this? What is this doing? Is well, not really alternating. This is really oscillating between -1 and 1. That means, in this case, towards the positive direction of infinity, we are having both limits up and down to be the bounds. Not like the previous example, the arctangent, because the arctangent is not oscillating. It's actually getting closer to pi over 2. But in this case, we have both bounds. So how do we describe this function? We describe it simply. It's bounded, simply bounded. And well, we specify that above by whatever value and below by whatever value. Well, in this case, those values above big M equals 1 and little m equals -1. All right. Sounds good?